Very well. Let's start our lecture number 10. In last class we talked about solution for Laplace equation in spherical coordinates, and in this lecture we are going to talk about the solution of Laplace's equation in cylindrical coordinates. We already have done that before when the potential depends only on r and phi. But now we are going to assume that the problem is within a cylindrical boundary or within concentric cylindrical boundaries, for instance, or perhaps flat surfaces also enclosing the region of interest. And now we have a problem governed by Laplace equation, and we are going to work on cylindrical coordinates. We're going to see that the differential equation generates what is called the Bessel functions. We're going to talk a little bit on the properties of those functions, on how they look like, what are the asymptotic behavior for low and large arguments. We're going to talk about orthogonality of these functions, in which context these functions can be orthogonal in the function space. And also we're going to talk about modified Bessel functions and the Fourier-Bessel transform. And finally, we're also going to make one type of expansion of Bessel functions, of the inverse function in terms of in cylindrical coordinates, which will involve one kind of, there are different ways of to expand the inverse function. We're going to show one of them how to do it. So it's going to give you an idea on how to do those things. This subject can be found in Jackson, sections 3738 and 311. That's where he talks about the expansion of the green function in general, or in the inverse function. And also African chapter 11 has an entire chapter dedicated to Bessel functions. So you can find more detail there. Okay, let's start with the Laplacian in I always get confused about Laplace's name for Laplacian. So don't worry about that. I will get used to it. Okay. So Laplacian of a potential in cylindrical coordinates can be written like this, right? Sum of three terms. 1 over r squared, right? Second derivative relative to z, relative to phi, and a final term, second derivative of the potential function relative to z. Now we are going to assume that the function is a function of three coordinates, right? And we are going to assume that this function can be separated as before, as a product of three FGH. F is a function of r, g as a function of phi, and h as a function of z. When we plug that into this derivative, we are going to, and already, you're going to have when we plug in here, you're going to have gh over r, right? Total derivative involving only f plus 1 over r squared times fh, total derivative of g, plus fg, total derivative of h, right? Then what we do, we divide by fgh, and we separate the term that depends only on z. We're going to get something like this, right? I mean, after we make the ratio, if we divide this by FGH, going to have this type of structure, a function only on R and phi, and a function only on H on Z, right? So again, we have to impose that both terms are constants, right? Because they depend on independent variables. This depends on R and phi. This one depends on Z. And we generate, for the second equation, we're going to generate something like this. I mean, it depends on the separation constant, right? We're going to call the separation constant for this situation. We're going to call it, let's say, a real number and a negative real number, represented by separation constant nu. Okay, so after we do that separation, I mean, this equals to minus nu square. We're going to get the differential equation that we are familiar with, e to h dz square, right? Minus nu square h equals 0. And this type of equation has solutions for real nu, real exponentials or hyperbolic functions. So we can say that h is something like this. Linear combination exponential of nu z or minus nu z, or hyperbolic, right, of nu z, or cosine hyperbolic nu z. Well, after we do, I mean, this part here, right, was separated from the equation, so we have left with something that contains this part here, and we have now we have again, right, we have this is the solution, right, we just mentioned to you. So if we go again, we're going to have now make a new algebraic step, and we're going to have, I can separate the radial part and the azimuthal part like this. And this one, we want to ensure that we have, I mean, typically we're going to have the full domain for phi changing from 0 to 2 pi. So we want to have solutions in phi that are periodic. So we're going to choose the separation constant for this function here equals to lambda squared. So that's going to generate this equation. Plus lambda is a second separation constant, right? So with that choice, I mean, choosing this thing here equals to plus lambda squared, we end up with this equation, right? And the solution for G, we know that is going to be, in general, right? We could use complex exponentials, but in this case, it's going to be easier to use sine and cosine of lambda phi. I mean, you could use exponential of j plus or minus j lambda phi, right? Now, if the full domain of phi is allowed from 0 to 2 pi, then this constant, which is in principle can be any real number, has to be an integer, okay? Including the value equals 0. So 0, 1, 2, 3. In this case, we don't have to use negative integers because we are talking about sine and cosine. So if we use negative integers, you just reproduce the function. If we were talking about complex exponentials, then we would change we could use the plus and minus values, right, for each integer value. So now we have a radial equation. If you look at the equation that we have, do a little bit of algebra, we're going to have this equation here, right? And we can work on it a little bit. Let's just do some algebra here. We're going to have something like this, r squared plus r plus, then you have nu square r square minus lambda square f. Because, look, I mean, we're making a particular choice for those constants, okay? Separation constants. Then we're going to see what are the, we're going to explore the solutions for this case. Then, after that, we're going to explore what are the scenarios after, if you had made a different choice of constants, okay? So let's solve this one first. Then here we can divide it by r squared. And we're going to end up, just make some economy here, right? 1 over r. Then I'm going to have also here, this is going to be nu square minus lambda square over r square, okay? And then we make a change of variables as before to make it, to normalize the solutions, right? I mean, you cannot, you're gonna use x. X is a variable, is not coordinate x. I'm using the same notation of Jackson. Perhaps I have to change to my own notation. Instead of x, we should use a different letter, right? Something like u. So it would never confuse with coordinates in the x, y, z system. But then we would go, mix with the UVW system. So sometimes it's difficult to find those additional letters. So let's keep with the x. So when you have that, you have ddr equals ddx dx dr, right? Which is dx dr equals to nu ddx. Here I can put nu square. I can factor it out. Can do something like this. 1 minus. Then here is going to be nu r square, right? Which is x square, right? So, so when you do that here and here, you're going to have, d2 dr square equals to nu square d2 dx square. Then we end up with nu square d2f dx square plus 1 over r equals to nu over x, nu over x, df dr equals to nu df dx. So it's going to be nu square plus nu square 1 minus lambda square over x square f equals 0. That's what we have. So just to gain some space here, I'm going to divide by nu square, right? We're going to end up with, we have this away. This is going to be 1 here. And this goes away. So that's the equation we get, which is the very well known by some people, not well known by everybody else, but by some people that work with those things. This is the very well known Bessel's differential equation. okay? So how do we solve it? Let me pass to the next page here. So what do we do now? Let's solve it, and again, the techniques that's due to Frobenius, right? Frobenius technique. Again, we're going to assume that f is a power series of x that starts at the smallest power. Dependence is x to the alpha power, the larger, the smaller one. So we're going to just assume that f is something like this. Have an infinite sum, okay? AI x I plus alpha. In this case, differently from the Legendre polynomials, we will see that because I mean, look, we have the range of R, which is x, right, goes from 0 to infinity in general, or to a certain size, to a certain maximum value of R. Okay. We might have singularities, either at R equals 0 or R going to infinity, depending on the choices. Okay. We're going to see that the traditional Bessel function that is generated as a solution of this differential equation doesn't have a problem of divergence. It doesn't diverge as Bessel functions did in the z-axis. We use that argument to truncate the Bessel function, the power series. We don't have that problem here, so we are not going to have that type of need, right, to truncate the series. We're going to have the infinite series, which is going to well represent the results. We're going to plot those functions, see how they look like. So when we do that, the first derivative becomes sum of ai plus alpha xi plus alpha minus 1, and the second derivative is going to be something like this, right? So what do you do? I mean, once you combine 1 over x, df dx, so we're going to have here I plus alpha minus 2, right? Same power dependence, so the indexes are matched. But we are going to have that term 1 minus lambda square over x squared times f, which equals to sum equals 0 to infinity ai, sorry, I'm going to put inside 1 minus lambda square, sorry, I'm going to have one term which is going to be ai xi plus alpha minus lambda square ai, I'm going to put inside, so it's like this, lambda square, right, ai, put like this, minus lambda square ai, so you can see better. So divided by the square is going to be y plus alpha minus 2. So these terms are similar, okay? This term here has the same power as this one and as this one, right? And this one, I had to look at I equals 0 and I equals 1, which is different. Then the remaining ones are the same. So let's rewrite this one. So it's going to be, we're just going to show the details here. So it's the same procedure that we just didn't do it in the Legendre case, but we can use the same, rearrangement of indices that we do. That's going to be A0 x to alpha plus A1 x to alpha plus 1. Then we go I'm sorry, it's not like that. Not like that. I mean, you have to look at these ones. The first two terms here, they go as x to alpha minus 1. I mean, sorry, x to alpha minus 1. There's one coefficient there, here too. Then you have x to alpha 1. X to alpha. Then you have x raised to alpha, x to alpha minus 1, right? Then we're going to have we're going to have power of x. This is wrong again, man. Just a second. We're going to have the lowest order power is going to be I equals 0. So it's going to x to alpha minus 2, x to alpha minus 1. Both, those things here. Then you go x to alpha, which is going to, be equal to this one. So we have to isolate, the term alpha equals I equals 0, I equals 1 for these three series here. It's going to be A0, okay? I equals 0, right? Alpha. This one is going to be A0. Alpha minus 1, right? Then I'm going to have this term here, minus lambda square A0, everything multiplied by x to alpha minus 2. Then have the next term, I equals 1. A1, alpha plus 1 comes from this one, I equals 1, plus A1, alpha plus 1, alpha, right? Then we have another term here, minus lambda square A1. Then we're going to have a power of x to alpha minus 1. Then after that, we can join all the series together, okay? So after this, we're going to have plus sum. I'm going to rewrite the index, okay? I equals 0 to infinity. So what I'm going to do is to say that I minus 2 equals to I now. I minus 2 equals to I. Then I'm going to have power of x minus 2, right? So I have to sum here 2, right? Because I'm going to start at y equals 2. So it's going to be a2, I'm sorry, ai plus 2, right? I plus 2 plus alpha, I plus 2 plus alpha minus 1. I'm joining this term here with this one here. So that's going to be the same thing, plus I plus 2, I plus 2 plus alpha, right? So I'm going to join everybody that has the same index. Then I'm going to have here I plus 2 here as well, minus lambda square AI plus 2, right? This one here. Then this is going to be AI here, plus AI. So everybody x raised to alpha plus I. Then I have to set everything here 0. So that's where we get our equations. For instance, this one here gives, if I look at this coefficient here, the first coefficient of x to alpha minus 2 equals to alpha cancels here. So it's going to be a0 alpha square minus lambda square. Plus, the next one is going to be a1 alpha plus 1 square minus lambda square, right? Then we have the other indices. It's going to be something like this. Then you can go and do some algebra in this thing here. So you have to set this plus sum, right, of I equals 0 to infinity, which is different, x I plus alpha equals to 0. So I'm going to make this equals to 0, this one equals to 0, and this one equals to 0. I mean, it's easy to see the result here. This one, you do some algebra, we are going to get this result here. So that's what we have. Right, and in the last case, I mean, when you do that, this term here, when we set this one equals to 0, we're going to have a recurrence relation given by this one. You see that if I set a 0 not 0, we have to choose, have to make this one equals 0 here. Alpha equals minus or minus lambda. But if I do that, A1 has to be set to 0, right? So if I do that, I have to set A1 equals to 0. In the same way, if I choose A1 different than 0, it means that alpha plus 1 equals to plus or minus lambda, right? Or something like this. Then if I choose A1 different than 0, then A0 has to be set equals to 0. So I cannot have both at the same time different than 0. These are equivalent solutions. I mean, it just means that I'm going to start at the given coefficients, then you're going to have the next elements in the sequence are going to jump by 2 units, A0, A2, A4, or A1, A3, A5. So these conditions are equivalent. I mean, it doesn't make much difference. Because if I make A1, right, not 0, you're going to have an increment of 1 here. So if I make A0, there's going to be no increment in the coefficient alpha. So so let's in practice use A0 different than 0, okay, and A1 equals to 0. I'll leave for the assignments for you to check that the conditions are equivalent. So it means that when you do alpha equals to plus or minus lambda, then the lowest order power is going to be x raised to plus or minus lambda. Then I going to have a simple relation like this one. I mean, a power series of the power difference by 2 units in each term. And if we set that the recurrence relation alpha equals lambda, right? And we do the cascade of this recurrence relation from a given coefficient, which is because you see, this is our all even orders. Doesn't mean that the power is an even power of x, right? So I can just do that. We're going to have this relationship between the coefficient at 2j, index 2j, and the coefficient, initial coefficient a0. We're going to have some, factors here, -1 to the j, factorial of j, 2 raised to j, and this productory here, we're going to have that one, right? So what is that? The productory is something like this. Let's do a little bit of algebra here. Productory from n equals 1 to j of lambda plus n. N is the discrete variable. This is equals to lambda plus 1, etc. until n equals to j, which is going to be lambda plus j, right? But recall that this is not a factorial, traditional factorial function, or a ratio between factorial functions, because lambda is a real number. Well, if lambda is an integer, let's say m, okay, recall that lambda comes from the variation in the azimuthal angle, and it's going to be an integer number if you have the full azimuthal variation allowed. So in many situations, lambda is going to be an integer. So in this case, the productory for integer lambda, have the productory like this, lambda plus m. Then we can use factorial function, right? And this one, we can use a ratio between two factorials. Yeah, the class notes are wrong here. I can see it. Well, lambda equals m. Oh, sorry, no, this is correct. I made a mistake here. Lambda equals m. This is a productory from n equals 1 to j. This is not lambda, is m plus n. Yeah, this is m in place of lambda plus n, and n is a variable, so it's going to be m, right? M plus 1, m plus j, which is the largest value, m plus 1, etc., m plus j. Now we have the ratio of m plus j factorial divided by m factorial. Because this is a productory, right? 1 times 2, etc., times m. And this one is 1 times 2, etc., times m plus 1, etc., times m plus j. Well, if we have lambda equals m, then we can use a factorial function. Otherwise, you have to use a function that's not a factorial function, but we have the well-known gamma function that can be used for this. Okay. Use the gamma function of a real or complex argument. In fact, the gamma function can accept complex argument. The only restriction is that x not equals to 0. Okay, x different than 0. And we can see that the property of the gamma function is this one. I mean, if you calculate gamma x plus 1, by definition, right, is going to be integral from 0 to infinity tx plus 1 minus 1 exponential of minus t dt, which is equals to t through x. Then I can do it by parts. We call u t to the x, and dv equals to exponential minus t dt, which gives us a v equals to exponential of minus t. So we do it by parts. It's going to be tx exponential of minus t from 0 to infinity. Minus integral from v equals to minus, right? So it's going to be plus integral of tx minus t dt. This one equals to 0 because at infinity the exponential is 0, and that's 0 for positive power of t, right? This is going to be 0 as well. So we're going to have gamma of, I think I forgot something. I forgot to calculate the derivative, right? The du equals to xtx minus 1. So we are going to assume that the x minus 1 is positive, so t raised to x minus 1 is 0. So we're going to have here, we're going to have an x comes from that one. So, and this one is gamma x. So we have x gamma x, right? That's the property. Gamma x plus 1 equals to x gamma x. So I mean, if we use that for the factorial, if you calculate, for instance, gamma of 1 equals to integral from 0 to infinity t raised to the first power, I mean t raised to the 0 power, exponential of minus t dt, which is equals 1. So gamma 2 equals to 2 times 1, right? Gamma 3 equals to 3 times gamma 2 equals to 3 times 2 times 1, and so on, okay? So if you go to Jack Afkin, there's an entire chapter devoted to the gamma factorial function in chapter 10 of Afkin, okay? So I have a detail on that. Let's make a plot. I mean, in fact, the gamma function is a function that equals the factorial function for integer arguments. So the idea is to have a fitting, you know, just show you here. So we have here the gamma function. There's a plot of it, okay? So you see that for integer values, the gamma function, which is the curve, is the curve that passes on the points which are the factorial, corresponding factorial values for integer values. So the gamma function is nothing less than a fitting function in between the points. Okay? So that's what we have for our gamma function here. So you see that when you use the gamma function, I can can replace the productory with a ratio of two gamma functions. Look at this. I mean, gamma x plus 1 equals to x gamma x, right? Gamma x plus 2 equals to x plus 1 gamma x plus 1, which gives me x plus 1 x gamma x, and so on, right? So if I go to gamma x plus j plus 1, we're going to have x plus j minus 1. So I'm going to keep reducing x plus j minus 2 until I get to x plus 2, x plus 1, then the last term is going to be gamma x plus 1. So if I make the ratio gamma x plus j plus 1 divided by gamma x plus 1, it's going to give me what I want. X plus 1, I'm going to invert x plus 1, x plus 2, etc. X plus j minus 1, x plus j, which is the productory from n equals to 1 until j of x plus n. So what I want is the productory. I want to make gamma of lambda plus j plus 1 divided by gamma of lambda plus 1 gives me that parameter that I have in my recurrence relation, which is something like this, lambda plus n, right? That's what I had before. So, so when we do that, we're going to have, you know, in summary, we're going to have integer value for lambda. The recurrence relation is going to comprise factorial elements, right, like this. And when lambda is not an integer, we're going to have the gamma function that appears in here, right? So the solution that we obtain for a given lambda let's choose the lambda positive value, right? Then we are going to have, can factor out part of the coefficients, and we're going to have this form here, and this factor here is going to be set to 1, and the power series that it results is going to be the Bessel function of first kind, an order lambda, which is a real number. So that's the general power series expansion of this function. It's just a power of x, right? A power expansion of x. Parity of the function is contained in the parity of lambda, because these are even powers here. Lambda, I mean, let's say that lambda is an integer. Lambda even gives an even function of x. Lambda odd gives an odd function of x, right? For integer lambda, we're going to have only, I mean, the lowest order power is going to be x raised to m, right? And the parity is the parity of m. The coefficients here, notice that they keep decreasing and decreasing and decreasing, right? So in the factorial function is something that goes exponentially. So you see that this thing is going to grow exponentially, so you have a substantial reduction in power series. So the series always converges for a positive m. For no integer lambda, we have a second independent solution, which is obtained by setting lambda into minus lambda. So just change the sign. We have a completely independent solution, j minus lambda, okay? And notice now that the lowest order's power is going to be this one here. So the series is going to diverge, depends on lambda, right? Lambda negative, positive number. I've already included the sign. You're going to have a power, inverse power, in fact, the lowest order. So you're going to have some divergence in the origin. That is okay, right? I mean, you have to avoid using the solution when your domain includes the z-axis, for instance, right? So these are linearly independent, two linearly independent solutions of the Bessel differential equation, unless lambda is an integer. Okay, I'm not going to lose a lot of time demonstrate that, but I mean the demonstration here is here in the class notes. I suggest you to do this, working this out, do the passages, you know, to make sure that this is correct. If you change the sign for an integer, lambda equals m, right? And change the sign, you're going to end up with a solution which is a copy of the original solution, okay? Because at some point the coefficients are 0. So you're going to, you can work that out. I mean, you do that. In fact, when you do some algebra, you show that for integer index, j minus m is a copy, okay, just with the possible change in sign, depends on the index of jm. Of course, right? M even is a copy. J minus m, m equals to gm. M odd is going to be minus jm, but it's a copy anyway. So these functions are not independent, and the way to do that, I mean, you can find that in detail, chapter 10 of Arfken. Okay, you can build the Neumann function, which is called the Bessel function of second kind, as this combination here. You see that if we have lambda integer here, this is exactly, you know, let's set here, let's pick this thing here, let's make lambda integer. It's going to be exactly, you know, integer lambda. Let's set lambda integer. This is going to be cosine m pi equals to minus 1 to the m. So this is, in fact, lambda equals to m. So it's going to be jm of x minus j minus m of x divided by sine of m pi, which is going to be, I mean, you can approach that, right? It's going to be a 0 here. So this is going to be 0 over 0. But if you make a limit process, you're going to have a limit. You would have to make the derivative of this function here, and the derivative of that function here, and the derivative of this one to calculate, calculate the derivative of the numerator using L'Hospital rule to calculate the limit. So the Neumann function is that limit when lambda goes to m. So you have an independent solution. That's how you build it. You build two, possible combinations, but you have this factors that make it possible to build a different solution. So when we do that, we have an independent solution, which is the Bessel function of second kind, which is the Neumann function. Okay. So let me show you how these functions look like. Let's start with the Bessel function. Let's just write this down here. Let's start with the Bessel function. Close this one here, of the first kind. So, oh, sorry about that. J, right? I think it's this one here. Yeah. So we have J0 is already showing there, right? I'm going to scan the index. You see that J0, Bessel function of order 0. I mean, this is the well-behaved function, right? It has is well-behaved in the domain, right? This is x, which is a measure of r, the radial coordinates. The Bessel function of order 0 is 1 in the origin, and it's going to be, I mean, the remaining ones are going to be 0. So you're going to have, I mean, you see that the roots of those equations, of those functions, in fact, the first root starts to get away from the origin, right? So I have those first ones. So Bessel function, first kind, is well behaved for positive x. This is for integer value. I'm going to put just here a fractional. You're going to have something that looks like a Bessel function. I can have a fractional index, right? 0.25 lambda, and I can put here minus 0.25. So you see that is a Bessel function. You see of I mean, this is a possible solution, a Bessel function of a negative argument, because it's not an integer. But if I put here minus 1, right, you have a replica of Bessel function of order 1, just with the minus sign, minus 1 here, right? Then I can put 2 here, and minus 2, no change, they're the same, right? So if I have 0.25, that's this function here, Bessel function of order 0.25, and minus 0.25, right, is a different solution. It's a Neumann function, right? So when you have those, you know, this is also a possible solution. It's not the same, right? So let's look at the, I mean, so let's go back to traditional terms. We're talking about Bessel function of positive arguments, positive order. They are all well behaved like this, right? Integer. So let's look at Bessel function of second kind. Let me close that one. Let me leave it open. Second kind is right here. So I have here already in the high index. So that's the second kind, diverges in the origin and is have undulation, right? Multiple roots. These are the features of these functions. You know, and the first root gets away from the origin when you do that. So you see, I mean, what is common to these solutions is that they have multiple roots. So recalling that functions that have multiple roots generally have orthogonality properties, right? Like the Bessel function, well behaved. You have the, you know, this one here. So they are the cousins, let's say, of sine and cosine, with the difference of this, let's say, this divergence. We have some properties I'm going to talk to you here. Let me show you let's look at my class notes. These are, I'm putting them all together here, right? And some important remarks that I have to look at. Bessel function of integer arguments is finite in the origin, is oscillatory, and is finite for large x. Second kind has singularity in the origin, right? Is oscillatory and is finite for x, large arguments. We have the roots of the Bessel function for order m. We can develop. I made in my course on workshop of computer modeling and simulation. I asked the students to develop an algorithm to find the roots, and in a single matrix, so you can find any root of those equations. So this is one important number for people who works with the optical fiber, is the V number that specifies when a fiber is going to operate on a single mode condition, optical fiber. So that root is important, 2.405, right? First root of the Bessel function of order 0. The roots, is important to be able to calculate the roots. You see that all the other Bessel functions have a root at the origin, but not the Bessel function of order 0, right? And also have the roots of the, of the Bessel function of second kind. We have some properties and recurrence relations that are common to all of those hypergeometric functions. This is the property I just mentioned to you. Can demonstrate, it's demonstrated in class notes. You can take a look and do it. We have those recurrence relations, which are important when you talk about orthogonality of Bessel function, calculate some integrals, okay? And here there are some asymptotic behavior. This is easy to infer, right? Because when we go to low power of x, let's say that m is an integer, the only dominant term in the power series is the lowest order term, and the lowest order term is like this, right? Modified Bessel function has this behavior. This is the lowest order term. They have x under in the denominator. Okay, so these are properties, important properties. And one important asymptotic behavior is this one for both j and y. I'm going to show you in practice. Okay, in the Mathematica. That the function behaves like a cosine function, except for the fact that the amplitude decreases, right? But I mean, you can use this to find the roots of this equation, which are the roots of the cosine and sine function. It's important to see the phase here keeps changing as the m increases. And also can construct Hankel functions, which are Bessel functions of third kind, because you see, I mean, j and y are like the cousins of cosine and sine, right? So you can construct combinations of those to build complex functions, which are the Hankel functions, right? They are the cousins of the complex exponential functions. J plus jy, j minus j lowercase jy. So we have the Hankel functions. So they are, the cousins of the complex exponentials. So let's just take a look at those asymptotic behavior in practice, how good they are, right? Let me show you here on the screen. let me show you on the screen, the computer screen. Let me close this. Let's look at the approximation of J for small arguments. Here we have some, let me just put everything to 0 here, starting value. We have here Bessel function of order 0, n equals 0. I'm gonna put the we are plotting the Bessel function on its asymptotic approximation. Let's see what that is here. Let's see. For small x, where is it? Oh, is it here? So in fact, I mean, J0 equals to 1 for small x. If you look here, for small x, m equals 0, the approximation is very rough. It's just a constant value, right? Which is going to be good at very small arguments. I mean, here, right? For very small x in this region here, let me increase the gain a little bit. So, I mean, up to, right? I mean, it's just J0 equals to 1. So we go to larger values, n equals 1, then you have the first approximation. The small x approximation is a linear function, which is going to depart very close to the origin, right? Then you go further, then we have some additional, let me just look at a little further when the approximation departs, right? So you see that you have a x squared, right? Second power and so on, right? I mean, as we go further in index, let me go further here, let me increase the gain. You see, I mean, you have a nice approximation up to 1.5. So, then you can go further and further until you see where they're the parts, right? Let me go a little further here. I mean, I can perhaps do more gain here, 200. I mean, up to 3, you have a nice, approximation asymptotic. But it's very nice to look at the asymptotic behavior at large x. I'm just giving you an example for the J function, right? For the J function is nice. When you increase the arguments, let's play those buttons here. Then let's put some high order. N equals 4. Let's look at more detail in the faraway range. With some gain here. Okay, so we have the approximation for the Bessel function, and we are looking at large values. Let me see here. Then go. Okay, so we have two functions here. It cannot be seen because they are right on top of each other. Let me see if am I plotting the two functions here? Yes. You see cosine and times the amplitude which decreases and the Bessel function here. Plotting the two functions, they are together. So, I mean, you can predict the roots just looking at the roots of the arguments. Sorry. Of the argument of the cosine function. Very nice, right? I mean, you cannot see differences here because they are, right on top of each other. If I go to low z, I'm going to have, I mean, because the approximation is not very good, you're going to see differences between the two functions and decrease the gain so you can see it. I mean, you see the blue one I don't know which one is which. Let me see. N equals 0. Let me change here a little bit. Okay. So you see, I mean, the one that diverges in the origin has 1 over root square of x is the approximation, and this is, the blue one is the Bessel function. Let me decrease the max here. You see? So those two things start to resemble each other, right? At very small values, but if I increase n, you see, so you can see noticeable differences. I can increase the maximum argument here to see where they start really to resemble each other. Let me see here. Do some gain. So you can see it. You see where we can resemble each other. So, I mean, the most interesting thing is the possibility of finding roots using the cosine function for large arguments. This is very nice, right? So, let's talk about the roots, which are very important in building orthogonal functions. If you look at the nth root of Jm, let's label like that. N is the second index, M is the first one. Let's assume that we have the whole domain. 0 is smaller than phi, is smaller than 2 pi. So lambda is an integer. You're going to have two independent functions, j and y. Okay, but j is the well-behaved one. So let's call that, let's call x and n the nth root of j. And I'm going to build, this is ordered like this, n equals 1, 2, 3, and so on. We're going to call this function Jm of x mn r over a when r equals to a, right? This function has a root. So, in fact, in the origin, we have j0. So, in the origin, w equals 1 if m equals 0, and w equals to 0 if m different from 0. Recall that in the plane z equals 0, the surface element, the sigma r, equals to r dr d phi. Integrations in r always involve the r dr element. So we have an orthogonality property of those functions, those w functions. If we define the scalar product in function space in the R domain as this definition here, f with g, f and g real functions equals to this integral. It can be shown that, we are not going to do that because there's a lot of algebra that is well detailed in chapter 11 of African, right? African. Chapter 11, that, I mean, those orthogonality relations, they are obtained by using the Sturm-Liouville theory of differential equations. So we have to use the differential equation to determine, you know, those properties. So that's an entire course on mathematical methods that we have in the graduate program, dedicated to that, to those demonstrations. Okay, so it can be shown that those functions are orthogonal in the domain between between 0 and a, and the orthogonality conditions can be written in this form. Okay. So when we use this property, this orthogonality property, we can always expand. So you see, we have to be able to find the roots of the Bessel function, have an infinity number of roots, right? It's a discrete set, but it's infinitely large, right? So if we collect all the functions together, then we can express a function as a linear combination like this, right? And the coefficient can be determined by doing the scalar product in function space. It's going to give you this one, which is explicitly calculated using this formula here. It's important to establish the completeness of this orthogonal functions. What we do is to plug back. We are going to plug this one sorry. We're going to plug this one back here. So we're going to use this expression here and insert in the sum. So the r variable we're going to change to r prime, right? So we don't mix things with this r here. So it's going to be r prime here. So when we do that, we see that, do that demonstration, right? It's just a matter of arranging the terms. So you see that this term here within brackets is the delta function of r prime minus r, because you see that in fact, sorry about that, not quite. This thing here is the delta function, right? Why? Because this thing here integrated together with f reproduces f. That has to be a delta function. So that's the completeness relation for the Bessel functions having this special structure, right? That's what we get. Okay. Also, you see that we are going to use this relation to also to explore when you have a very large very large domain, right? Look that notice that we are talking about functions in the domain within a cylinder, looking from top here, right? That has a radius equals to a. So we can imagine, all functions have roots in the rim, in the cylindrical surface r equals a. I can imagine if I increase further and further a, make it as large as possible, what would happen in the expansions? So that's very similar to Fourier transform, right? I have Fourier series on the finite domain, and you keep increasing, you get to a Fourier integral. The summation becomes an integral. So let's consider that. Well, what is the completeness relation for a very large A? Okay, let's take a look at that. So let's take a look in this relation, this completeness relation here. 1, which is this one, right? For a very large A, right? So we're going to set xmn over A equals to a continuous variable A. Why? Because the distance between roots for a very large A, the increment in this number for large A is a differential change in k, right? So that's why we have that. So let's see what happens in the limits A very large, the orthogonality conditions. Let's write it again. That's what it is. Now xmn has been replaced by k, right? xmn prime by a different value, k prime. So on the right hand side we have the limit of the normalization constant, which is a squared over 2 jm plus 1 square of xmn. So when this is large, argument is large, right? So what happens, you see xmn equals to k times a. When a is large, we have large xmn. What happens? So the location of the cylindrical wall gets larger, and the root's going to be displaced, right? So for large Ka, what happens? So you can use the asymptotic behavior of this function here, which resembles a cosine function, where we just showed it on the tables. So I have to calculate xm plus 1 at the nth root xmn. So we can just plug that inside of the cosine function and inside of the roots, right? And recall that here we can use Ka. Recall that we want to calculate the square, so it's going to be 2 divided by pi times k times a. And here we have cosine square of this argument here, right? Now we notice that xmn is the root of jm, and here we are calculating jm plus 1, right? But xmn is the root of jm, so it means that the cosine, right, of xmn minus m pi over 2 minus pi over 4 equals to 0. And so the cosine of this thing is 0. This is wrong here. M plus 1, right? So there's a mistake here. This m pi over 2 I mean, this factor here is xmn, which is here, minus m pi over 2, which is there, minus pi over 4, which is here, minus pi over 2. So there's a mistake here. This is minus pi over 2. So cosine of this minus pi over 2 equals to sine of this term here. Sine of this thing here. Right? But because cosine equals to 0, right? Cosine equals to 0 means that sine equals to plus or minus 1. Right? So this factor here is equals to 1, which is plus or minus 1 square. Right? So the normalization factor is something like this. Jm plus 1 square at the roots of the Jm equals to this number. So when you put that in the limits, I mean, you see that the upper limit went to infinity here, right? So you have this limit here, and this delta n prime. First of all, this is going to be delta n prime times this limit, right? Let's call this number a prime. So let's make a prime finite. If n not equals n prime, this is 0, right? For n not equal to n prime, n different than n prime. So it means that the integral is going to be 0. And for n equals n prime, the integral is going to be 1 over k. This is important because k is a parameter here, right? You cannot put the k in the limit there. We have to look at least the behavior. Even if the number is large, but depends on 1 over k. On the other hand, a prime, which is a over pi, pi is a number that becomes infinitely large, right? So you can say that it's infinity. So if the index are the same, k and k prime, we have something that's infinity divided by k. And if it's different than k different than k prime equals 0. So it means that we have this integral relationship, 1 over k delta of k minus k prime, because k different than k prime, the result is 0, k equals k prime, infinity divided by k. And this case is important to ensure the dimension, right? The dimension. You see that the dimension of delta in k space is 1 over k, right? So the dimension of this factor here is 1 over k squared. So see, the dimension is important to consider that. I mean, I have an integral that has dr, r, Jm of kr, Gm k prime r equals 1 over k delta of k minus k prime, right? So what's the dimension of the left-hand side? Length times length. This is a-dimensional, so this n length square. The dimension here is 1 over k, and dimension of delta is 1 over k, so it's 1 over k squared, but kr is a-dimensional, so k has a dimension of length to the minus 1, right? So 1 over k squared has a dimension of L squared. So everything is correct. So that's an important completeness relation for, you know, unbound integration involving two Bessel functions. There's a very nice, very important completeness relation that we are going to employ it. Okay? So in summary, I mean, we are using lambda real, either integer or non-integer, right? If we have, in summary, the solution that we built is a product of three functions, right? The radial dependence relies on either Bessel function of first kind, Bessel function of second kind, or Neumann function if lambda is real. If lambda is an integer, you can use, I mean, if lambda is integer, you're going to have to use a Neumann function instead of y, right? Otherwise, you can use those y functions here. For this type of problem that we chose, I mean, for this type of choice, we have periodic function in phi and hyperbolic functions in z. You can use exponential also, right? Okay, so that's one aspect of the problem. Let's talk about modified Bessel functions. So we go back to the differential equation. The first step was to choose a separation constant. We chose minus nu square. If we had chosen plus nu square, we would have a periodic solution in Z now, right? Second type of solution. Still, the solution in the azimuthal variation is still periodic, but now we have a periodic solution in Z. We will be able to identify when to use, you know, one type of solution or the other one. Okay, but let's look at this type of solution here. We're going to have, oh, this is totally crazy here. What is this? This is phi, right? So this is phi also. Sorry about that. That's fine, right? Now, the radial solution is going to be obtained by setting, I mean, because you change the sign of the square of nu, right? So I have to set nu into j nu. We are going to have real functions, or at least at the most real function times a pure imaginary number. Because you recall that Bessel functions that we built, they start with x raised to lambda, right? Or x raised to minus lambda. Then you go like this, x0 plus lambda, x2 plus lambda, etc., right? Let's say that lambda is even. So you're going to have x equals to nu r, right? If I'm not mistaken, x equals to nu r. So you're going to have jr to lambda, jr to lambda plus 2. If lambda is even, right, lambda even, all of those numbers are real. If lambda is odd, integer, right? All these numbers are proportional to the real powers times j. It's easy to calculate that. Because odd powers of j is a multiple of j, right? So you're going to have, at the most, when lambda is even, you're going to have complex imaginary proof number times a real function. So you can build real functions by doing that. And that's how we do it. The results is Bessel functions of a complex of imaginary arguments, purely imaginary. Okay. Recall that nu is going to be a real number. We're going to talk about real numbers because nu gives the periodic variation in z. We're going to have a periodic variation. So nu is real. And then, we build those functions, completely real functions, the modified Bessel functions, because now we have Bessel function of imaginary arguments. To make entirely real functions, have those functions here, just to multiply by that. If lambda is even, this is going to be 1, right? Otherwise, it's going to be pure imaginary number. And the same way, you can build the first, the I function, modified Bessel function, and the k function, by doing a similar, combination between first kind and second kind. So why we do that? To make real functions. So now we have something that's similar to the case of complex exponentials. When you change the argument to real arguments or complex arguments, you have complex exponential and real exponentials. Sine and cosine instead of hyperbolic sine, hyperbolic cosine. So that's the behavior. Let me show you on my screen here. How these functions look like. They are exponential type functions. Sorry about that. What is this? Oh, it's right here. I came here, right? Close that. There's the modified Bessel function. Of first kind. This is, I'm changing the index. I'm just using the integer index. So it looks like an exponential function, right? It's not exactly the same. Because for n equals 0 looks like exponential, which is 1 in the origin, but then all the others are 0 in the origin, right? Modified Bessel function of first kind, function I. And you have the modified. What happens here? The modified Bessel function of first kind is well behaved in the origin and diverges for large x, large arguments. And the modified Bessel function of second kind is the other way around, is the decreasing exponential, right? Well behaved for large x and divergent for small x. you have those, they go even further, larger in the origin as you go for higher indices. So they are just look like traditional increasing and decreasing exponentials, right? They cannot be used, for instance, for a function expansion. They are not orthogonal. They are not wavy, right? No undulation, no oscillation. So they are used for other types of solutions. You know that we have asymptotic behaviors. They are not listed here, but you can find in the, African, you can have, you have some information here, right? We have some properties here. So all the Bessel functions modified of the first kind are 0 in the origin for m different than 0, right? Well, that's the behavior for large x. They look like exponentials, but they have this factor down here. This might be interesting if you want to do some approximate calculations, and just look at x very large. This function, the second kind, modified function of second kind, is like this for large x. Okay. Let's see what else we have here. Okay. So for this choice of separation constants, we're going to have what? Modified Bessel functions in the x, in the R domain, right? Either we have to exclude solutions that diverge when you clearly know that it shouldn't diverge. For instance, the zx, you have to avoid, for instance, the modified Bessel function of second kind. Dependence in phi is going to be periodic, and dependence, sorry, this is z again, another error there, hz equals to that, periodic as well. So recall, nu is the index related to the z variation, and lambda is the index related to the phi variation, right? So we have two types of solution in summary. Type 1 is the one that gives oscillatory functions in the radial domain, oscillatory solution in the phi domain, and hyperbolic variation in the z domain. In the type 2, we're going to have exponential-like solutions in the radial domain, and we have periodic in the phi and the z domain. Okay? So we have to be able to decide which functions to use. Here is an example of using type 1 solution. So again, if you have the full variation of phi involved, you're going to use integer values of lambda. So suppose that we have this problem inside of the cylinder in which the potential is given at a height z equals L. The lower cover of the cylinder is grounded, phi equals 0, and the lateral wall is also grounded. So we're going to solve the problem inside of the cylinder. So you see that the potential is grounded on the cylindrical surface. So clearly, the solution that's going to work here is the one that has periodicity in phi, lambda integer, right? The one that has also a 0 in the r equals a wall. We have to use oscillatory functions relative to r. We wouldn't be able to do that by using this type of solution here, right? Because these are functions that you cannot combine to have let's say, a finite value in the origin and a 0 value at r equals a, because I have to use I and k. One of them, k, diverges in the origin, so I cannot use it. So it has to be oscillatory. So if we set lambda equals to m, then we have to impose that at r equals to a. In fact, it's like this, right? The function is type A. I'm going to write down here. You see that we have a superposition of solutions, but let's pick just one of them. Let's call it phi m, okay? So I have here a coefficient am, jm of r, right? Plus bm, ym of r, or nm. In fact, I'm going to use, I think I'm labeling n, right? Let me check here. The Neumann function. Neumann function, where is it? Neumann function. I think I'm using yn, irrespective of the index. Yeah, I'm using ym as the second solution. Okay, I'm using ym, is the Neumann function, Bessel function of second kind. So then here we have, I'm going to put all the constants here. Cm sine m phi, like this, plus dm cosine m phi, and I'm going to put another constant em. Then I'm going to have a hyperbolic sine of here, in fact, is not, I mean, we are calling this nu r, right? Still haven't done anything here. Sorry. Nu r, we still don't know what it is. Is it? Something like that. Nu z plus fm cosine of nu z. So if you look at the problem, I'm going to just draw here quickly, right? Z is I equals A. So the potential is grounded at z equals 0. So we have to ensure that at z equals 0, this function here is 0, but this one is equals to fm. So we're going to have fm times this other thing here has to be 0, right? Anywhere in 0 smaller than r smaller than a, or 0 smaller than phi smaller than 2 pi, means that I have to make fm equals 0, so you don't have the sum, right? The second consideration is that the function has to be well behaved in the z-axis. So the Bessel function of second kind, which diverges in the origin, is not present. So then we have, you see, we have only one term here, am times fm, have a new constant. We are going to put all these constants in here. So the function becomes jm of nu r, right, times hyperbolic sine of nu z times, then we're going to have cm sine of m phi plus dm. So I have two constants, in fact. Two constants for each m, right? Cosine of m phi. So we have that. Then we have to go to r equals to a. You see that at r equals to z equals to L, this is going to be a constant value. But we have to go to r equals to a, and we have to ensure that the function goes to 0. So what happens? Jm of nu a equals to 0. So it means that nu a is a root of the Bessel function of order m. So we're going to call it xmn, and I'm going to label the roots as we talked about before, starting at 1. So nu is xmn over a. So the functions are Jm of xmn r over a, which are the Wm of r, right? These are the functions we spoke about before earlier, that they are orthogonal within the space r between 0 and a. So, in fact, we have, recall now that the dependency in z now becomes sine, hyperbolic sine of nu, right? xmn over a times z. So the solution that we have so by doing that, I mean, we can go, just now go quickly. I mean, the solutions, we have two indices, m and n, okay? This is just an example from one type, one element of the solution, but we know that we can make a superposition of solution. Let's try that. And then we have the proposed solution is something like this. See? I mean, I already went through this thing here, right? I already applied the boundary conditions. So I have an infinite sum in two indices. Okay, I already did that. M goes from 0 to infinity, and n goes from 1 to infinity. So I have coefficients to be determined. So we have to force that at z equals L, the function becomes this given function. For instance, V equals V0, a constant potential, right? It's an electrode and raised at the V volts. There's a function. You can put two electrodes plus V or minus V in half of the surface of the circle, have V, in the other half minus V. So have different possibilities. Let's call it V of R phi. So it means that when you go to Z equals L, there's a proposed solution. We force the sum to be V of R phi. Okay, that's the thing here all together. We're going to use the orthogonality of the periodic functions. We're going to call those functions sine is um, cosine is vm. These functions have well-known orthogonality properties we talked about previously in the course. They are orthogonal, right? The sine functions, when they are equal, the integral goes to pi. U and v, cosine and sine, they are orthogonal. And v depends if the index is 0 or not. It's going to be 2 pi if the index is 0 or 0 otherwise. Okay. So you can also do this thing here in a single equation. It's going to be 2 pi. It's going to be pi times delta m prime 1 plus delta m 0. So when seeing this, the canonical delta, if m equals 0, gives 1, so it's going to be 2 pi, right? This thing gives you pi. If the canonical delta equals 0, this gives pi. Equals 0 if m is not 0, if one of the indices is not 0, right? Can also do that. So I have the orthogonality properties. Oh, sorry, I'm a little. Yeah. So we have, just recalling that the function that we have is the WMN, which has definite orthogonality properties we talked about earlier too, right? Orthogonal. What we do is to make when you go to I equals A, let's do it here. You have to impose the VR phi equals to sum of n equals 1 to infinity WMN. I'm going to omit the arguments. Then we have hyperbolic sine of xmnl over a, right? Then we're going to have am plus bm vm. That's what we have. We are going to build those functions umn by definition equals to wmn times and the v, capital V, wmn times vm. By doing that, we can without losing a lot of time, can just formally calculate the coefficients, right? We do the dot product of u with the function. We're going to isolate a single term, right? Only term mn. So you're going to find the a coefficient. So you're going to have this hyperbolic sine the normalization constant of the WMN, I'm going to put like this. Then I'm going to have AM, UM. The same thing if you want to calculate, I'm sorry, this is the U function, right? Sorry about that. This is correct. V function. You can also calculate VMN with V. This repeats. This is going to be BM, VM. So this is easy to calculate, right? So you have formulas for BM and AM, so you solve the problem, right? So you have the solution outlined here. So use all those, orthogonality conditions outlined here, so you can find, from this scalar product you find AMN, from this one you find B. So here's the results. Recalling that the coefficients of the sine functions for n equals 0 are always 0, because sine function is 0 for n equals 0. And I have those, in practice, I have to calculate integrals involving the function given at z equals L. That was the type 1 solution. Type 2 solution would happen when we have two grounded surfaces in the lower and top surface of the cylinder, and we still have an arbitrary function lateral in the wall, right? If you have an arbitrary function in the wall, then you have a type 2 function. Because now we have two instances as a function of z where the potential goes to 0. So we have to have two roots. It means that we have the periodic function in the z direction. Also, I have an arbitrary function at r equals a. It means that I have to expand relative to phi. Okay. Now, notice also that we have the z-axis included, so the radial function cannot have singularity at r equals 0 in the z-axis. Okay. So the function for this case is going to be the modified Bessel function as a function of r, and you have those new functions here, U, and capital V, which are, you know, simple definitions. Sine times sine in Z. Well, why is that? Because that's the function that has multiple roots. This function has 0 at z equals 0 and z equals L. Okay? So you do that homework to make sure that you find that solution. So again, it's easy to calculate the coefficients, right? We have those orthogonality conditions. I will leave for you to do this calculation. Then you have the solution for this type 2 problem. Okay, so it's a matter of calculating those integrals represented as scalar products. Well, we have another powerful device now. Which is the Fourier-Bessel integral, which is the same. I mean, we just showed you that we can expand functions in the radial domain using those normalized, those orthogonal sets of functions, right? The question is this: what happens if we have the problem in the cylinder, right? Radius A, potential is grounded on the wall. If we let the top surface go to infinity, okay, but we have to guarantee that the potential goes to 0 at infinity. If we make the height goes to infinity, so it's like an open cylinder on the top, and make the lateral wall go to infinity, it means that we are giving the potential in the plane z equals 0. So what's the solution on the upper hemisphere in cylindrical coordinates? That's the problem, right? So let's keep still the function at finite a, finite radius. The z dependence has to be a decreasing exponential. We're not going to use hyperbolic functions because the function has to go down as z goes very large, right? We're going to use the periodic functions in phi, and to guarantee that the potential goes to 0 on the wall, just use that special function, Bessel function, the well-behaved function that has a root at r equals a. So the problem is this: given the potential in plane z equals 0, what's the potential in the upper hemisphere? Given that the potential dies away for large z. Okay. Well, we had the solution of something like this for finite a. What's going to happen now is that, as we did before, we're going to have this ratio here becomes a continuous variable because the roots, they are distant by discrete amounts, but divided by a, the change in this variable is continuous. Okay. So instead of summing in the index of the roots, we are going to integrate in the k variables. Okay, so those coefficients are going to be dependent on the. I mean, they depend on the order of the roots. They're going to depend on the variable k. So the sum, I mean, the sum in n is going to be an integral. Okay. And it can be cast like this. I mean, in fact, you could propose, I mean, you could do the problem inversely. We could propose this solution here and plug into the equation, differential equation, Laplacian equals 0. We would find that this combination solves the Laplacian equals 0 because we are going to end up with differential equations that are satisfied by the azimuthal functions by the functions that vary with z, and by the radial function, which is the Bessel function. So that's a possible solution. You can always write like this. Okay? Well, how do we determine those coefficients, A and B? Well, orthogonality. Okay? For instance, for the sine, we can determine the coefficients for m different than 0, because the coefficient is 0 for m equals 0. So recall that A0 equals to 0, okay? So we just make orthogonality. We multiply by sine function on both sides and integrate from 0 to pi. Okay, so this is 0. We determine one integral relation. We don't determine the coefficient, but we determine that this integral is given by a given number, which is this calculation here. For m equals 0, you can calculate the integral for b coefficients. For m different than 0. Now, you see that our unknowns are in the integrals, b0, bm, and am. Now we go to the completeness relation that we derived earlier today, which we just demonstrated, right? This relationship here is very important. Why is that for? Well, I'm going to integrate in k-space on both. You know, I'm going to multiply each integral by Jm of k prime. And I'm going to integrate into the R space. So in both dimensions, right? I multiply both by Jm of k prime, right? In fact, yeah, and we integrate the radial coordinates. When you do that, if we use this property here, we're going to isolate a single term, either am or b0 or bm, because of the delta function, right? So that's how we solved for each coefficient, using that completeness relation. So we find then how to determine the coefficients. So now we have this problem, given the potential at z equals 0, the solution for any z larger than 0 is something like this, with these coefficients calculated from those integrals. Solved, right? Very well. Now to conclude our lecture, finally, right? So over 2 hours. We also have similar expansion of the green function, of an inverse function, in fact. Cylindrical coordinates. Well, it's important to expand in several situations because the inverse function is always present in different problems, and expanding it in the normal modes of a given coordinate system is a very useful tool. Okay, so I'm just going to write down here what is the expansion in cylindrical coordinates. I mean, there are different types of expansions. Okay, this is one of them, involving the modified Bessel functions. Let's see how it goes around. The inverse function can be expanded as a Fourier integral, in fact, involving the modified Bessel functions. You see the product here. We have complex exponentials, so it means that you see modified Bessel functions arise when you have periodic function in z and periodic function in phi. So we have a modified Bessel function in R. That's why like this. So we have periodic function in z, periodic function in phi, and have Fourier-Bessel type integral here, right? R smaller and R larger is the smaller or larger between R and Z. And recall that x and x prime in cylindrical coordinates are given by those decompositions, right? R in the radial direction and Z in the Z direction, and the corresponding prime variables. Let's recall that the inverse function is one type of green function, right? It has that property that we know we derived before, that the Laplacian of inverse function of any green function is minus 4 pi delta, in particular for the inverse function, right? This is true as well. Let's decompose the cylindrical, the delta function in cylindrical coordinates, right? That's the decomposition. Let's use the completeness relations so we can expand the phi dependence and the z dependence using complex exponentials. Well, we have a completeness relation in terms of the phi functions, right? Why? Well, why some? Because in this case the domain is limited between 0 and 2 pi. So it's Fourier series, and Fourier series has a completeness relation relative to the summation side, right? In the z function, well, we see that z is and z prime are unlimited. So z, the delta function, has a completeness relation relative to the Fourier integral, which we derived before, right? That's the completeness relation. So we can replace this part of the delta function by those expansions, right? So we have this form of the delta function, and then we plug this into the differential equation, which is the Laplacian of G equals to that. Okay? So what do we have then? It means that if we have an expansion on the right-hand side in terms of variables phi and z, it means that the function here can have a similar expansion with the same basis functions, right? And if we expand g in the same way as we did for the delta function, we can equate term by term. That's the beauty of orthogonal functions. When you expand a function in orthogonal functions and have an equality between two different sides having the same expansion, you can simply equate coefficients, corresponding coefficients on each side. It's the same as this. If a vector has a given decomposition, a1, b1, c1 in a basis, and a second vector has a decomposition b1, b2, and b3 in the same basis, if those vectors are equal, it's because each decomposition, each component is equal. That's the same thing in functions, right? That's the beauty of using orthogonal functions. So when we do that, it means that the inverse function can be expanded. We're going to use those coefficients here to by convenience. Why? Because in the delta function, we have the 2 pi square here, right? So we're going to use the same, we're going to use a similar definition. We're going to keep the 2 pi square here. We're going to have an expansion in terms of orthogonal function in the z space. And I think there's something missing. Oh, it's right there. And the orthogonal function in phi space. And a coefficient that we don't know what it is, but it's a function of the two parameters, right? Let's apply now the Laplacian on the inverse function, now that is expanded like this, right? So we have a combination of derivatives. The radial derivative only acts on Gm, right? This part goes out, as well as the exponential is not acting on the exponential, is outside here. And the other derivatives, which are the derivative relative to r and phi, gives these results here, right? you see that d squared, the second derivative of exponential of jm phi minus phi prime equals to minus m squared times the function. That's where the m squared comes from, right here. Right? The k squared comes from the second derivative of the exponential function, eigenfunctions, right? So when we do that, we obtain, I think there's some missing thing here. Oh yeah, no, this is right. That's the second, the right hand side is this thing here, right? And the left hand side is this thing here, this complicated thing here, has lots of terms, right? But I mean, you see that we can compare term by term. It means that the term within brackets, this one here, which is the coefficient of the complex exponential in phi and the complex exponential in z, has to be the same coefficient, right, which is the sum here. So it means that we have this differential equation for the radial function, okay? So we have to solve that problem. Well, let's start solving it for r different than r prime. So we have an homogeneous solution. The second hand gives 0. The left hand side gives 0, right? And then we have this differential equation here. And if you look at it, we immediately recognize as being Bessel's differential equation for one specific choice of separation constant, which is the choice that gives modified Bessel functions as solution, right? So these are the solutions that give Im and Km of Kr, okay? So Gm can be written as a function of r. For r smaller than r prime, we have a combination of Im and Km. Let's call it psi1. We have a coefficient which should be constant, but depends on r prime. Let's call ar prime, right? And for r larger than r prime, we have a coefficient that depends on r prime, and a second combination of Im and Km. That's how it is. Let me just talk to you about those equations, okay? Let's say differential operator, let's call it d, times a function, applied to a function, this is a Laplacian, right? Something like that. Equals proportional to the, let's say, delta r minus r prime, right? What happens when we solve these problems is that we obtain a continuous function that has a discontinuous derivative at r equals r prime. So the behavior for r smaller and r larger than r prime is something like this. Green functions, which are those functions governed by equations like differential operator equals to a delta function, they always have this behavior. They have a continuous value at the transition point where the delta function has a singularity, right? I mean, they have a continuous value, even have a delta function on the right hand side, right? But you have discontinuous slope, right? You're going to see that evidently every time you have a delta function on the right hand side, you're going to have a discontinuous slope and a continuous function. Okay? So that's what happens here. So just recalling, we have as our function something like this. But we see that, I mean, for r smaller than r prime, the function has to be well behaved, right? So the solution for r smaller than r prime has to be a modified Bessel function of the first kind. That's the one that has no singularity in the origin. And the function for r larger than r prime has to be a modified Bessel function of the second kind, because that's well behaved for large r. So the function that we have to use is something like this for r smaller than r prime, and something like that for r larger than r prime. There's another important property that is always explored in solving problems like this, like expanding functions and determining green functions, is that the green function, we're going to see that further in additional lectures. The green function has the symmetry property. Okay, if you change the argument, the green function doesn't change. I mean, that's true, right? The inverse function has a magnitude which is independent on the order of x and x prime. Okay, so it means that gm of r prime has to be gm of r prime r. So it means that if I change the arguments of the first, you see, if I change r into r prime here, I have to get this result here. So it means that AR IM of R prime equals to BR prime KM of R. And this solution is satisfied, right? If I have to do that. I mean, this function has to be that one, and this function has to be this one. So A is in fact Km of Kr, and B is Im of Kr. And Gam is in fact an amplitude Im of Kr smaller and Km Kr larger, which are, as usual, the smaller are less than, right? Is the smaller, and r larger than is the larger between r and r prime. So that's the structure of the solution. And now all is left for us to finish the problem is to determine A. We know that A has a structure which is this one, but we don't know the constant. The constant is handled by integrating the delta function around, integrating the differential equation around the singularity on the right side. That's why the delta function is used for. Integration on the delta function makes it possible to determine a value, right? So just integrate around r equals r prime. On the right hand side, you're going to have a 4 pi over r prime. In fact, the integration is like this. This integration is I can simply integrate, right? It's okay. I just integrate well, when we do integration around r equals r prime, you can keep the r here if you want. But if you do the integration in the limit, okay, because you see we are integrating on a very narrow region across r prime, okay? So on one side we have r prime plus, so r is a variable, right? I'm integrating r across r prime. So we're going to have values picked at r equals r prime plus and at values r equals r prime minus. Parts of the left-hand side are going to give 0. If we do the integration here, this term here is not going to contribute anything. This one here is going to be 1 over r prime, and we have the derivative of this thing here on the one side and the derivative on the other side. So that's what we have. We have this continuity in derivatives, okay, if we do the derivative of the function there, so we're going to have, recall, that's for larger, R larger here is R, so the function is Km, the one that depends on R. So the derivative of Km, the K factor, which is in the argument of K, goes out of the derivative, right? And here we have the derivative for R is less than R prime, so it's the derivative of I, okay? So recall that A has to be positive because we are talking about the magnitude of the function. Whatever we do here, the final result for A has to be positive, okay? Those derivatives are those things here. Okay. And in fact, what we have is two independent solutions, and we have the C here, which is called, for in the Sturm-Liouville theory of differential equation, this is called the Roskian of the differential equation. And for Bessel function differential equation, the Roskian, which is this thing here, I mean, I'm not going to go to the detail on the lecture notes. They are in here, the next page. But the Roskian is proportional to 1 over R as well. So if we calculate the Roskian, I calculate A, okay? It turns out, I mean, I'm going to leave it to you, the demonstration here. It's very straightforward, but just take some time to do it, okay? So I'll leave it to you. After you do the Roskian, calculate everything, you go and show that the constant, the Roskian is 1 over x, where x is the argument of the Bessel function, and it gives you a final value of A equals to 4 pi, which is the last step in determining the expansion, okay? So when we do that, we demonstrate the original relationship, which is the expansion of the Green function, or the inverse function, in terms of complex exponential in phi, right? Complex exponential in z, and modified Bessel functions. And that's our expansion. I ask you to do all these passages. It's important to do those calculations so you get training on the subject and a better sensibility on how these things are, you know, besides of connecting your neurons a little more. So that's the idea of doing all these calculations. You might think it's pointless, but I mean, in the advanced science, in engineering, in physics, and in those related fields, we have to be able to understand how to do those calculations. Sometimes we need those to make a device, and that's why it's important. Okay, so I will stop here, and see you next time. Bye-bye.